Dear students, in this session we will discuss push down automata. In short, we'll call it as PDA. So push down automata. As we know that we have FA, finite automaton, for representing the regular languages. In the similar manner, we have these PDAs for representing the context-free languages. First of all, we will look at the model of FA. In the model of FA, we have a memory which store the input string, okay, which we will read from left to right. There will be associated reading head with the help of which we will be performing this reading operation. There will be a finite state control which will tell us what will be the current state of FA. So suppose if I have written Q0 here, it means that Q0 is the current state. And this read head tells me that this symbol in the input string is under the read head. So I am reading this symbol. So depending on in what state I am and what symbol I am reading, I will decide what state to move next. So I will change the state as per this symbol and this state. So that state will be changed and then reading head will be moving one position to the right. So in this manner, I will be reading my input string from left to right, and whatsoever input symbol I am reading and what is the current state of FA, as per this, I am taking this decision to what state I should move. So this is the model for a finite automata. In the model of PDA, we will be having all these things in the same manner. Additionally, we will be having one more memory in the form of a stack, which we will call it as push down store, PDS. In short, we will be calling it as PDS. So it is the push down store. It is in the form of a stack. So when it is in the form of a stack, when we will be reading from this memory, we will always be reading from the top of the stack. And as per the function of PDA, we can also write to this memory. So that's why the head connected to this memory will be a read-write head. Head connected here is a reading head only, because we can only read from the input. We cannot modify the input. So that's why it is only a reading head. While here we are having read-write head. We will read the top element of this push down store, and as per the transition function of our push down automata PDA, we will write something over this push down store as well. So there will be three functions. We will change the state as per the current input symbol and current top of the push down store, and we'll change the state, and we will write something over this push down store. So in this manner, our PDS will function. So basically, PDS is an extension of our FA model. This addition is in the form of a stack. So an additional memory we are having. So it is a more powerful machine than the finite automatons. So that's why its capability of representation is also higher. So that's why FA only able to represent the regular languages, while our PDA is able to represent context-free languages as well as the regular languages. Now we will discuss the formal definition of a push-down automata. A push-down automata, suppose named as A, is a collection of 7 things. So it is called a 7 tuple. So these 7 things are Q, sigma, rho. This symbol we will use, we will call as rho. So Q, sigma, rho, delta, Q0, Z0, and F. Now we will see what does these symbols mean. So Q, capital Q, it is a finite non-empty set of states, as it was in case of FAs. So it is a finite non-empty set of states. Then sigma, it is also similar to the FA. It is a finite non-empty set of input symbols. Then come on the third one, that is the rho. This is a finite non-empty set of push-down symbols. So as we have discussed in the model of PDA, that we are having an additional memory which we are calling as push down store, which is in the form of a stack. So there are certain symbols which can be pushed over this stack, or which this stack can hold. So all the symbols which this additional memory push down store can hold, will be called as push down symbols. So all push down symbols will be stored as a set. That set is called as the row. So this row is the finite non-empty set of push down store symbols. Then come on the Q0. So it is the start state or the initial state, as in case of FA also. So there we were defining start state as Q0. As Q0 is a state, so certainly it will be the part of capital Q. Capital Q is the set of all states. So Q0 will be a member of this particular set. So Q0 will belong to capital Q. Now Z0 is the initial push down store symbol. So among the various symbols which can be stored over the push down store, this Z0 is a special symbol which is called as the initial push down store symbol. Whenever we will start the functioning of PDA, this initial push down store symbol will always be stored on the push down store. So this will be initially present on the push down store. That's why it is called initial push down store symbol. Now come on capital F. Capital F is set of final states, as in case of FA. So in case of FA also we were having the final set of final states. So in the similar manner, our PDA will also have some sets which are designated as final states. So all such states will be collected into a set which is called capital F, the set of final states. Certainly, as all states are collected here, so it will be a subset of capital Q. So all states will come from Q, so it will be a subset of capital Q. Now come on the last one, that is the transition function delta. It is a transition function, as in case of FA we were also having the transition function which was telling us that corresponding to each state and each input symbol to which state we should go next. So in this similar manner, there is a transition function for PDA as well. Now in FA, our transition function was from Q cross sigma to capital Q. Okay. So our first input was a state, our second input was a input symbol, and on the basis of these two we were deciding what will be the next state. So output was a single state. Now in case of this PDA, our input comes from Q cross sigma union null cross row. So means there will be three inputs. First input will come from a state, that is Q. So we will see in what is the current state of our PDA. Then we will see what input symbol we are reading. Okay. So what input symbol? So what input symbol from sigma we are reading. We can also make transitions on null symbol as well. Means without reading any symbol from the input string, that is equivalent to the null move in the epsilon and f phase. Okay. So meaning thereby we can take null moves also here. Okay. So and the third input will be from row, that is the push down store symbol. So we'll check what is stored on the top of the push down store. So on the basis of these three things, what is the current state, what input symbol we are reading, or we are taking a null move, means without reading anything from the input, and what is on the top of the push down store. So on the basis of these three things, we will make our transitions. What will be the output? The output will be a set of the finite subsets of Q cross row star. Q cross row star means it will give us two outputs. First output will be a state. Means we will come to know what is next state we should go. So we may change the state. So what will be the next state? It will tell us. Then row asterisk means row asterisk. It is a string of push down store symbols only. So there will be a string which it will output. Basically, what we will do, we will take the topmost push down store symbol, we will consume it, and then we will write a string of push down store symbols over the push down store. So we will push certain symbols over the push down store. So output of this transition function will be a state and a string which we will be writing over the push down store. So input are a state, current state, what symbol we are reading or the null move, and what symbol is on the top of the push down store, and output will be the next state which we will be moving, and then the push down store symbol that we will be pushing over the push down store. So this kind of transition function we will be having for PDA. One very important thing regarding the transition function is, as in case of FAs, NFAs or epsilon NFAs, we are bound to write our transition function for every state and every input symbol. Okay. Now here that bindation is not here. Suppose delta QAZ is phi for some particular input symbol, then we will not mention it. As QAZ, Q is a state, A is a input symbol, and Z is a push down stored symbol, which is the topmost push down stored symbol. So depending on these three things, we will take any one of these actions, because output is a new state and the symbol to be written. So and it is a set of the finite subsets of Q cross sigma rho star. So meaning thereby, among these multiple available pairs, we can take anyone. So in this manner, we can say our transition function delta for this PDA is a non-deterministic function. So the nature of this PDA by default is non-deterministic. In FAs, we were having the variants DFA, that is deterministic finite automata, NFA, non-deterministic finite automata, and epsilon NFA, which were allowing null moves as well. So here we can see that null moves are also allowed. So non-determinism has come from this fact also, and non-determinism has come to this fact also, that among the multiple available choices, we may choose any one of them. So whenever I am in the state Q, reading a symbol A, and at the top of the push down store there is the symbol Z, I can either move to the state Q1 and writing alpha 1 a string over the push down store, or what I can do, I can move to the Q2 state, or I can write the string alpha 2 over the push down store, and so on. So among these multiple choices, any one of the choices I will take at a time. So in this manner, my PDS functions. So my PDS or my PDA is non-deterministic by default. It allows null move as well. And wherever delta QAZ is equal to phi means this is empty. This set, because this is a set, so this set may be empty, as in NFAs, we may have the set of states which are reachable, maybe the empty. So in the similar manner, it may be the empty. So wherever it is empty, we will not mention it. So this is all about the formal definition of push down automata. As we have understood that if delta QAZ is equal to some pairs of new states and strings which can be written on the push down store, and among all these available pairs, suppose we have chosen this one. Okay, so this simply means that if we are currently in the state Q, reading a symbol A, and Z is on the top of the push down store, so we will be erasing Z, and then we will be moving to the state Q dash, and we will write alpha, or we will put the symbols present in the alpha to the push down store. So these all symbols will be pushed over the push down store. So basically we say that alpha is written on the push down store. Is it? So in this manner our PDA functions. In case this alpha is null, in case this alpha is equal to null, so what effect comes? So we change to the state Q dash, and as Z symbol we have erased in the processing, and we are not writing anything. We are writing null means we are not writing anything. So simply this symbol, topmost symbol Z, get erased from the push down store. So this is the effect when alpha is equal to null. So this is an important point, and we call such moves as the erasing moves. And all other moves when alpha is not equal to null, these are called as non-erasing moves, because we are writing something over the push down store. So we are not decreasing the length of the push down store. If the length of alpha is 1, we are maintaining the length of push down store. If the alpha is containing more than one symbol, then we are increasing the length of the push down store. One more important point is that PDA cannot make transitions if PDS is empty. Push down automata cannot function, cannot make transitions if push down store is empty. Push down store means the memory which we have attached in the form of a stack. So that push down store is empty. how push down store may be empty. Suppose we are performing certain erasing moves and we erase all the symbols which are present over the push down store, then push down store may become empty. If push down store becomes empty, in such a case our PDA will halt, it will not function further. Okay, so this is an important point. This is called halting of PDA. To better understand the concept of PDA, which we have just discussed, we are taking now one example. So suppose our PDA A is a collection of 7 things: Q, sigma, rho, delta, Q0, Z0, and F, where capital Q is Q0, Q1, and Qf. So our set of states is consisting of 3 states, namely Q0, Q1, and Qf. Our sigma contains 2 symbols A and B, so all our strings which will be the part of this language will be formed from these 2 symbols A and B. And rho is A, Z0. So as we have said here also, Z0 is the initial push down store symbol, so it should always be part of rho, and additionally A is also present there. Okay, so now from this example we can understand that there may be the common symbols between the sigma and rho. It is not required that rho and sigma cannot contain the same symbols. They may contain different symbols, as well as they may contain certain symbols which are common among them. Okay, so it is also possible. So A is also present in the input symbol, so it is input symbol as well as it is a symbol which can be pushed over the push down store. Okay, so this is a push down store symbol as well. Now F is consisting of a single state, that is the Qf. So we say that Qf is the final state. So among these 3 states, Q0, Q1, and Qf, this Qf is declared as the final state, and this Q0 has been declared as the start state. So this Q0 is the start state and Qf is the final state. Now transition function delta is given by these transitions. Okay, so you can look that these transitions are in the required form, Q as Z. So there are 3 inputs and 2 outputs. So inputs are, first input is from the state, another input from the input symbol, and third input is from the push down store. So it is the topmost push down store symbol. And outputs are the next state which we will move, and the string which we may write over the push down store. So this string may consist of only the symbols which are present in the row. So A or Z0 can come only in these strings. Okay. So now let us see how, what function or what language this particular PDA is accepting. So this PDA is accepting the language L is equal to A to the power N, B to the power N for N greater than equal to 1. So we know that it is a context-free language. So this PDA which I have written here represents this language. Now let us check how it is representing this language. Just we take a string of N is equal to, suppose 3. So not 3. So suppose, yes, okay, 3. So the string will be triple A, triple B. So let us see this string will be successful over this PDA or not. Just we will start from the start state Q0. Okay, so we are in the state Q0, reading the first symbol A, and there will be a push down store, and always our push down store will start from the initial push down store symbol Z0. So this is the current status of the push down store, is it? So this symbol A we are reading, Z0 is on the top of the push down store, so this is the topmost symbol. So we are in the state Q0, Z0 is on the top of push down store, we are reading an A. So this transition will be valid. So according to this transition, we have to move to the state Q0. So we were already in the state Q0. So now also we will remain in the state Q0. So state will remain same, Q0. Okay. So state will remain same. So here I am writing the state Q0. Okay. And then I am removing the symbol Z0 from here and putting AZ0 here. Okay. So when I put AZ0 here with A, the leftmost symbol on the top of the stack. So Z0 will be pushed here and A will be pushed here. So now this A will become the top of the push down store. Okay. So now what is the situation? I am in the state Q0, reading the another symbol, next symbol, that is also A, that is also A, and now on the top of the push down store is A. So situation becomes Q0, A and A. So Q0, A and A. So this transition will be valid. So I will be using this transition, and as per this transition, I have to remain in the state Q0, so I will not change the state. And then I have to write double A. So I will, before writing this double A, I will remove this topmost push down store symbol. So I will remove this A and I will write double A. So means I will be pushing these A's. Okay. So this will be the situation. And now this A will be the current top of the push down store. Again, I am seeing the same situation. Q0 is my state. The next symbol is also A, and push down store top is also A. So Q0 A will be the situation. So again, this will be applied Q0 A. So I will remain in the state Q0 and by removing this A and putting it double A. So basically, I will be pushing one more A here, and this will become the top of the push down store. Is it? So I have done this. Now, next symbol I will be reading. Next symbol will be B. So I am in the state Q0. Next symbol is B, and on the top of the push down store is A. So it is the situation Q0BA. So I will look here where I am finding Q0BA. Just look here. I am finding Q0BA. So this rule will be applicable. So as per this rule, I have to change the state Q1. So from Q0 now I will be changing the state to Q1, and I have to write null. So before writing null, I have to remove this A. So I will remove this A, and in place of this A, I will be writing null. Null means I will not be writing anything. So basically, this symbol A, the topmost symbol A, has been erased, and my top will come to the next symbol, that is also A. That is the second A. Now I am reading the next symbol B. So now I am in the Q1 state, reading the symbol B, and on the top of the push down store is A. So I am getting the situation Q1BA. So I will look here, Q1BA I am finding here. So means this rule is applicable. So as per this rule, I have to remain in the state Q1, okay, and I have to write null. Means basically I have to remove the topmost symbol of the push down store. So means this A will be erased and my top will move down to one position, the next. Okay. So then again I am reading the next symbol, that is again B. So I am again getting the situation Q1, B and A. So again this rule is applicable, Q1, B, A. And I will remain in the Q1 state, and writing null means I am erasing the topmost symbol and my top is coming back to this Z0. So now situation is, I am in the state Q1, my whole input string has been processed, meaning in string I am having nothing. So what I will write from the input string, I will be, what I will read from the input string. So I will be reading nothing but the null. I can read nothing from the input string because it has been exhausted. So Q1 state, null from the input string, and on the top of push down store Z0. I will just try to see whether I am having any such rule here. Yes, I am having a rule here, Q1, null and Z0. So Q1 is the state. From input string, I am not taking anything, and Z0 is on the top of the push down store. So this rule is applicable. In this case, I will move to the state QF. So I will move to the state QF and I will write null. So meaning thereby I will remove the topmost symbol, that is the Z0. So this Z0 will be erased. And as this Z0 will be erased, our push down store will become empty. And as push down store will become empty, our PDA will halt. So our PDA will halt in a state which is a final state. So that's why this string, this input string will get accepted. So this will be the part of the language defined by this particular PDA. So AAA, triple B. In the similar manner, you can test whether AA, double B will be accepted or not, single A, single B will be accepted or not, 4 A's and then followed by 4 B's will be accepted or not. So you will look at, it will accept all the words of the form A to the power n, B to the power n, where n is greater than equal to 1. So now we have seen that how our PDA will function, how our PDA will define a particular language. With this example, I also want to demonstrate one very important point. As we have discussed that our transition function is of the form delta Q A Z is equal to a set of pairs, and each pair will have two things. First thing is the state, and another thing is a string which we can write over the push down store. Here in our example, if we see, we are always having a single pair. We are always having a single pair. Means there is no non-determinism. Means if I am in the state Q0 reading an A, and on the topmost symbol of the push down store is Z0, then I am bound to take this option. So I will be remaining in the state Q0 and writing an AZ0. So because there is no other pair present here, only a single pair is present, so I am bound to take this pair. So there is no confusion. If suppose there are more than one pair present here, as this is the case, so I am having the choice. Either I can choose this one, I can choose this one, or I can choose this one. Okay. So this is creating a non-determinism. So here where I am having only a single choice, there is no other option, means it is deterministic. What will be my next course of action, what will be next state, and what will be the next status of the push down store. So then such a PDA is called deterministic. So we will discuss how we can define a deterministic PDA in more detail in the next lecture. Thank you.